Hello, everybody. We're just gonna get started. We're just getting started. Let's see. Let me try that. Okay. I just took my medication. Steven, how are you? It's been a while since I saw you. I wasn't doing so well. How are you, Steven? My music. Hi, my music. Hi, Steven. Steven, why are you up so late? Ben Abraham, hi. My music, hi. Steven, I'm good, still working on book 5. Shalom, shalom, shalom. Good morning, good evening, good afternoon. Oh, you can't sleep. Cool. Hi, J-Dub. Ben Abraham Steinment, how are you doing? Shalom. J-Dub. Hello. Hello, hello, hello. Just closing my medication cap here. Make sure it's tight. I don't want any kids to get into that. I'm gonna... Oh, you're 6 hours ahead. Okay. I think. How have you been, you guys? It's been very cold and snowy in Boston. And indeed, I have been under the weather. I'm still kind of recovering and feeling a bit tired. But I wanted to say hi to everybody. And hopefully we will resume our usual lives here soon. And this weekend, Saturday, Sunday, it's gonna snow or be really, really cold. So I am going to be planning to do some of my longer, all day long lives where we hang out and do studying and discussing and all that. All that. Let's see, is there something in my eye? So, hopefully I see you there for that. Shalom, everyone. I haven't gotten a lot of snow here, is what Steven is saying. We're getting quite a bit of snow here in Boston. So I have a lesson plan for this weekend where I'm planning to do some longer lives throughout the day. My plan will be to spend mostly on doing the live with you guys because it's gonna be very cold and or snowing, so we're gonna be snowed in and doing a long live, okay? So that's my plan, and I hope I see you this weekend for those long lives. We can hang out together. Thank you everybody for joining. Hi Hughes. Amor, Mio, hello. Hughes is saying, you're beautiful, thank you. Hi Eddie. All right, so I'm just setting up the live. Please do like, share, and subscribe, everybody that is joining. And let me also share the live from my other phone. Amor mío. Okay, guys, let's see. Hello, Eddie Bertho is saying my love. Okay. Well, thank you, Eddie. I will do a super chat goal. Let's start that. I will share the live. Thank you, Steven, for telling people to like and subscribe. Hi, Eddie Bertho. Hello, Eddie Gonza. You need my number? Already have my ring. Thanks for your suggestion. Oh, did you get a ring from that thing I shared? Ben? Or do you mean you already have a ring because you're married? I don't know what you mean. You got the ring from that place, EPI Jewelry? Really? That's great. For Valentine's, really? Oh my goodness. Your wife is gonna be happy. You got the ring? Wow. Wow, wow, wow. That is unbelievable. I'm happy for you. Hi, Jonas. Amore, love. Amora is love. Amore means without gain. With the exception of Greek, amora is synonymous with tax. Amora, love. Okay. Okay. Let me pin my comment. Sounds like Pepe Le Pew. Okay. All right. Can you guys like and subscribe in the meantime? I'm still setting up my live monitor for a second here. So, let's see. Tonight's gonna be a short live. I hope you like, share, and subscribe. Help with our goal here. Let's see. Where's the live monitor so I can click the buttons of the buttons. This is not a religion podcast. It is. Actually, Ben, I'm gonna make you a mod, if that's okay. You can relax as well. Don't worry about don't have to mod too much. Just relax and listen to the physics and don't worry. Don't worry. Steven, I'll make you a mod too. Okay, perfect. Steven, you're also a mod. Thank you guys. Like and share and sub. Okay, I did that. Baji's here. Baji is here. Okay, so we had remember how we talked about the Kaluza-Klein theory in regard to general theory of relativity and string theory, and we will continue with that for a little bit before we go to bed. Okay, that's the plan. That baseball guy. Okay, so let me do the following. Okay, everything is very slow. Let me tag the book so that people will know what book it is. It might not be something that is on here. It may not be here. I'll tag that one just so people have something. Okay. Have a good night. Guess multiverses. Thanks. Thanks for the key. I'm not gonna stay long. I'm sleepy too. Okay, let's just do a few minutes. I know we're late today. Late tonight. So basically, remember how Kaluza and Klein had introduced one extra dimension. Here's Baji, by the way, and kind of proposed that to Einstein. And now Einstein has to kind of react to that. Okay, the fifth dimension. Remember about the fifth dimension, the unification through symmetry. We're looking for a grand unified theory, all that stuff. So we're gonna just read about that for a little bit, for a few minutes, okay? And discuss that for a few minutes. So Einstein hedged his bets. If the Kaluza-Klein theory failed, then he would have to explore a different avenue toward the unified field theory. So this is the unified field theory we're talking about. At that point, shortly after general theory of relativity was worked on by Einstein in 1915, around that time, there were really only two fundamental forces, gravitation and electromagnetism, that they knew about. Both of them are long range. Remember how there's also two more fundamental forces that now we know about. These are strong nuclear force and weak nuclear force, but those were not discovered yet. And what they knew is that there's also this thing that is up and coming and making progress, which is, of course, in that century, quantum mechanics. And there were a lot of things about quantum mechanics that they didn't really like. And they wanted a more overarching unified field theory, which can explain all of this in an elegant way. And the way they were hoping to find this unified field theory is, of course, by means of symmetry. And symmetries is something that has helped Einstein in the past as well. And so he's kind of looking to do the same thing again and see how that kind of goes. And meanwhile, Kaluza and Klein have done something by taking his general theory of relativity and extending it to include one more dimension. Now, this is going to be an extra spatial dimension, which they propose as being very tiny and curled up. And so it's hard to see and hard to detect. And that's why we may not experience it normally, is what they are saying. But it led to a beautiful unification with electromagnetism of gravitation, and so they were excited about that. But what is yes, a theory of everything. So hi, mental health. Thank you guys very much. So let's see what Einstein's reaction was and why there might have been sort of a hesitation. Okay, so his choice was to investigate geometries beyond Riemannian geometry. So by the way, let me define something for you really quickly. This is something we have defined before, but I just wanted to remind you, okay? And it's a little difficult for me to get all the words, and so I'm just gonna Google it. Or sorry, I'm just gonna look up the definition. So remember how I mentioned earlier that general relativity is done with a different kind of mathematics and a different geometry versus our usual geometry, okay? Which is why it can be a little difficult for people to grasp it and for people to understand what we say when we mean by the four space-time and the four-dimensional general theory of relativity. Hi Vivek, hi Mr. 6293. How are you? Thank you for coming, thank you for attending the live. Can you please like, share, and subscribe? So we mentioned earlier about how Einstein did his general theory of relativity with four space-time. So this is a four-dimensional geometry. And basically the mathematics and the way you do things the mathematics that the way you do things is kind of different than what we're used to, which is the Euclidean geometry. So let me read to you essentially the difference between Euclidean geometry and Riemannian geometry. So Euclidean geometry describes flat spaces where parallel lines never meet. So this is the type of geometry that we're used to, where we generally, when we go to school or when we do various geometry exercises and all the math, and where there's three-dimensional space and time is not treated in that same way as a fourth dimension in that same way. All that geometry, when we do it, it's generally Euclidean geometry, okay? So this is the type of geometry where flat spaces are spaces where parallel lines would not meet, okay? This is what we learned, remember, in geometry, when we said parallel lines don't meet, and remember all the trig and all of these things, and we learned about sides of the triangle and all that stuff, all that geometry, all of that, basically. Moderators, are you here, or are you asleep? Thank you, Stephen. Okay, so that's where we learned the Euclidean geometry, okay? So now let's see where it's different. So Riemannian geometry generalizes this sort of thing, but to the curved spaces or manifolds, like the surface of a sphere or the fabric of space-time. So Riemannian geometry is basically kind of like Euclidean geometry, but it works for curved spaces, or what we sometimes call manifolds, manifolds. So the surface of a sphere is such a curved space, it's not a flat space, right? Or in fact, even the fabric of space-time. So remember, Einstein is treating the four space-time as his dimensional as his dimensions, as his geometry. And so that too is actually going to be a curved space-time, because remember also that gravitation leads to a curved space-time. It makes the space-time bend. So gravitation, or a massive object, its gravitation is responsible for the bending of space-time, and this bendiness of space-time is going to be sort of this manifold in general theory of relativity, which can be described with Riemannian geometry. So the mathematics that Einstein has to do or did is Riemannian geometry, not Euclidean geometry, okay? So just keep that in mind. So anyways, okay, we will keep going. Thank you so much everybody for joining, and please do like, share, and subscribe. So the parallel postulate will fail in Riemannian geometry, allowing for different geometric rules, for example, triangles, angles, some to more than 180 degrees. So some of those rules we learned in Euclidean geometry, which we thought as the, gospel, as the ultimate, that's not going to actually hold for Riemannian geometry. And we will have a different kind of straight lines. There are certain sort of analogies though between the two. So for example, straight lines in Riemannian geometry is going to be something like what we call geodesics. So if you go to my live, I believe I called it Einstein's equations, we actually set up the basic mathematics for general theory of relativity, and we define something called geodesic, and we define something called metric and things like that. And these are basically concepts out of Riemannian geometry. So the people, mathematicians who might have worked with that a lot would not find that to be totally new, okay? So essentially, Euclidean geometry is flat and Riemannian is curved and more general, encompassing Euclidean as a special case, okay? So this is just out of the internet. So you can look up yourself what Riemannian geometry is versus Euclidean geometry, and the spelling is Riemann. Okay, so essentially this curviness of space-time and the four-dimensionalness of space-time that Einstein worked on, the Riemannian geometry allows him to do that, and he basically defined gravitation as a bending of space-time, okay, where space and time are the dimensions. Now, Kaluza and Klein took that and extended it to include one more extra dimension. So even though that sounded pretty crazy, or not crazy, but a bit bold back then in 1916, 1917, I think it was 1921, 1925, by the time this was becoming something that people knew about what Kaluza and Klein did, it was actually kind of conservative compared to, for example, string theory later on. Superstring theory basically requires 6 or 7 extra spatial dimensions. So this is sort of the little bit nascent stage of string theory, if you will, what Kaluza and Klein were doing. And they were, of course, trying to come up with a more unified field theory, or a theory of everything, okay? And this was what Einstein also was working on, and he, in fact, died trying, okay? So this is quite an important subject, of course, to those people who worked on these classical topics. And of course, there's also the people who worked on quantum mechanics and quantum topics, and those people were busy with that. But then everybody else probably was trying to make some head or tail of the bizarre world of quantum mechanics, and how to unify that with general relativity. And even to this day, as we know, there is no real explanation of gravitation in quantum mechanics and particle physics. And I mean, if there is, I'm not aware of it, or I know people are working on quantum gravity and things like that, but there is no conclusive sort of particle nature of gravitation as far as I know. It's not been discovered. And so as you know, we are still not really successful in unifying the 4 fundamental forces. The 3 non-gravitational ones, electromagnetism, strong nuclear force, and weak nuclear force, are still unified. We have made a lot of progress in unifying them, especially in other regimes when it comes to energy, temperature, and all that stuff. So those are unified. But so for example, we think in the early universe, shortly after the Big Bang, probably these forces were unified. It's just that gravitation seems to have kind of split up with the other fundamental forces much earlier on, and we still don't fully really get where gravitation would have been unified and how to explain that. How is there a theory of mathematics that will unify all four? But at that point, remember, at the point of 1915, 1916, 1920s, at that point, not all the fundamental forces were even known about. Remember that the neutron, which is a part of the nucleus of the atom, wasn't even discovered until 1932. And so the other thing there was that Einstein and some of these other people were, of course, missing a lot of information. Here they were being a little bit worried about the bizarre nature of quantum mechanics and desiring for a unified field theory or a theory of everything which can subsume quantum mechanics and gravitation and everything and not be so weird like quantum mechanics, according to them. But I mean, according to everyone, but I like both. I like quantum mechanics as well as gravitation. You know, I'm fine with both. But basically, they wanted that. But at the same time, just know that they were a bit ahead of their time, but that is normal for a lot of great people. You know, they're of course ahead of their time. They're trying to do something that is really difficult, and they're trying to do something that might, well, truly was rather impossible, because if you don't know all the things that you'd have to unify, then you cannot unify them. But at the same time, that's kind of how science works, is you make progress and then you discover new things, and then you realize, oh gosh, I have to revise my thing and I have to make more progress, and I was wrong because I didn't know about this thing. And that is the nature of scientific discovery and progress. So there we have it. So but Einstein did think that the Kaluza-Klein situation of including one more extra dimension and how beautifully it unified gravitation and electromagnetism was very, at least very intriguing. But what he did with it, that's what we're reading about at the moment. So his choice was to investigate geometries beyond Riemannian geometry. So basically, he was a bit worried that as much as it was tempting to accept the fifth extra dimension that Kaluza and Klein brought to him, he was worried that it may not ever exist. What if it did not actually exist and we never found it? So if you say that your theory just depends on and requires this extra dimension, which is so tiny that we don't experience it, and it's this curled up, teeny tiny, introverted dimension that nobody experiences, that is all well and good mathematically, but experimentally that can lead to speculation, because people can say, well, I guess we'll never discover it and we'll never be able to confirm it. And that can be detrimental for the credibility of that work. That is, I would say, the biggest problem with string theory even now. So because the extra dimensions that it requires are still not testable. So basically, Einstein knew that, okay, well, we've done Riemannian geometry, even though it's not taught as widely in our schools and stuff. In primary school, we all learned the Euclidean geometry version of geometry, where the parallel lines don't meet and stuff like that. But Riemannian geometry is basically like that, but for curved spaces, and rules are a little different there. So he's thinking that, well, I learned some Riemannian geometry to make this general theory of relativity work out, but maybe there should be, even more mathematics. And this is why one of his famous quotes is that he had math problems, because he did, right? Basically, his math problem was maybe he hadn't done the math, well enough to unify everything and find the theory of everything. Maybe imagine you're sort of a genius mathematician and physicist, but there's this one thing you're trying to do which is really difficult, and your math doesn't allow it yet. You might think that there is a deficiency in your mathematics and whatever approach you're taking in geometrically, which is holding you back. So I think this is exactly what he thought. So he consulted with many mathematicians, which is of course the right thing to do. And I will note that I really think that Einstein was a very good student of other people and their work. If he wasn't a good student, there's Suji. If he wasn't a good student, then he wouldn't have known certain things. And I was mentioning the other day earlier, a few days ago, because we go live a lot, by the way. If you're interested in these topics, we have recorded many, many, many such live stream episodes on physics topics under the live tab of my channel here. So basically, he never would have gained his deep insights with the speed of light in vacuum being a constant and things like that in special theory of relativity if he wasn't a very, very good student of electromagnetism. He wouldn't have seen the discrepancies between the fact that special theory of relativity, the whole speed of light thing being a constant, and Newtonian mechanics were in disagreement if he wasn't also a very good student of Newtonian mechanics, right? So he's a very, very good student, and he was also a good student of mathematics, and that's how he got the theory of relativity, the general theory of relativity, which of course includes significant mathematics worked out. So for this theory of everything business as well, which is what he has his eyes set on next, after general theory of relativity, he wants to now come up with a theory of everything, or a unified field theory. So he consulted many mathematicians, and it became quickly obvious that this was a totally open field, as in there was basically unlimited work really that one could do on this. In fact, at Einstein's urging, many mathematicians began to look into post-Riemannian geometries, or the theory of connections, to help him explore new possible universes. So everybody, at this point, he has also won his, I believe he has also won his Nobel Prize. So, he's a well-reputed scientist doing great work. He did not become, thank you for becoming a member, J-Dub. J-Dub417 has become a member. Thank you so much for your support, becoming a member and everything like that. Thank you so much. Hi, Manny. Let's see. Hi, Northern Versus. So electromagnetism is not ether. We ruled that out. So a lot of people thought it was ether in the late 1800s, but by early 1900s, by the year 1905, Einstein gave a special theory of relativity as an explanation of how light works. Light is an electromagnetic wave. It can travel just fine through vacuum. So we don't need ether for the light waves to travel, okay? So he gave us an insightful look into light with his special theory of relativity. Thank you, everybody, for being here and for liking the live. Please do double tap to like the live, like, share, and subscribe. Thank you, Daniel. Thank you, Pixel. Thank you, Northern. Thank you, Young Nebula. Hi, Pixel again. Thank you, Rap. Unsolved work, yes. This was unsolved. This theory of everything, or the grand unified theory, or the unified field theory. Hello, DP3718. Hello, Sleek. Hello, Friendzone Millionaire. Thank you so much. Let's see. J-Dub, thank you again for becoming a member. Really appreciate you. If people want to support me with my goal in the live, that is much appreciated as well. Hi, Antonio. Hi, Skinwalker. Hi, John. Somewhere now. Is this that new or so-called AI? Okay, I don't know what that means. Thank you guys for being here. I'm literally from you. Okay. Four-dimensional geometry is Euclidean geometry extended into one additional dimension. Perfect. Dimensional less numbers are real. What is your positive advice for the world? Hi, T and Trucker. So, where are you from? We're in Boston. There is Baji behind me. See, Baji right there. The Martians knew everything way sooner than Earth people. Okay. Thank you, young Nebula. I love your username, by the way. We've talked about Nebula as well, Nebulae as well here on the channel. Please do come back to our lives. Hi, Solara. Okay, so basically, to answer the question about ether, I think I just did. No, we don't need ether for electromagnetic waves to travel. Electromagnetic waves or light waves, because light is an electromagnetic wave, can travel just fine through vacuum, okay? So, and we got an excellent sort of work on this, which is special theory of relativity in the year 1905. And so in that same year, Einstein was extremely productive that year. He gave us like 4 papers, brilliant work in that same year. And then he got the Nobel Prize in photoelectric effect, of course. They didn't really understand relativity very well. So they gave him the Nobel Prize for photoelectric effect, okay? So by the time he's doing general theory of relativity, of course, he's famous. People know him quite well. He has quite a lot of credibility. And so, of course, people are happy to kind of join him and help him out and support his theory of everything efforts. Now, that is until, of course, certain other things also affected all of this, by the way. Where is my sentence? Basically, you know, as you know, the 20th century also had the 2 world wars. So those wars also affected what kind of physics got done and what sort of distractions people had at that time, okay? So theory of everything, or the this unified field theory, was a big dream of Einstein's, but unfortunately wasn't fulfilled, and also it was derailed quite a few times, okay? So anyway, mathematicians helping him. So working on post-Riemannian geometries was a nightmare, however. Einstein had no guiding physical principle to help him through the thicket of abstract equations. Because also remember that Einstein was a very intuitive scientist. Even though, of course, he was really good at math compared to the average person, I would say, because again, very good student of all these topics he was. He liked to be able to imagine something, like his thought experiments. Remember his thought experiments? He liked to be able to really just like imagine the physical picture of something, right? Like racing against a beam of light, or how things would act under gravitation versus if gravitation was not there. These types of things, symmetries, equivalences, those types of thought experiments really propelled him in his best work. And so when you ask him to just kind of make the geometry more and more difficult with abstract equations and things, that's not really intuitive or a thought experiment at that point, right? It's more of this tedious exercise. So it was a little rough. So previously he used the equivalence principle and general covariance as compasses. Both were firmly rooted in experimental data. He had also relied on physical pictures to show him the way. With the unified field theory, however, he had no guiding physical principle or picture. So, you know, this is what I was saying. So curious was the world about Einstein's work that a progress report he gave on the unified field theory to the Prussian Academy was reported to the New York Times, which even published parts of Einstein's papers. So at this point, he's quite famous, okay? Soon, there were hundreds of reporters swarming outside his home, hoping for a glimpse of him. Eddington wrote, "You may be amused to hear that one of our great department stores in London, Suffrages, has posted on its window your paper, the 6 pages pasted up side by side." So he's gotten advertising going on for him in London so that passers-by can read it all through. Large crowds gather around to read it. Einstein, however, would have traded all the adulation and praise in the world for a simple picture to guide his path. So he was quite determined to get this unified field theory, which became his full-time passion, really. And even though he had become quite famous and had all this adulation at this point, that's really what he was after, okay? Gradually, other physicists began to hint that Einstein was on the wrong track and that his physical intuition was failing him. The thing is, like, even when you're successful, there is no dearth of critics. And the moment you sort of show any weakness or vulnerability, people can actually start to take away from your credibility. Even if you once did genius work, people could be quick to judge and be like, oh, maybe he's getting old now, and what's he done recently, things like that. So nobody is really immune from that, even Einstein, okay? So one critic was his friend and colleague, Wolfgang Pauli. Of course, we know about Pauli, one of the early pioneers of the quantum theory, who was famous in scientific circles for his unsparing wit. You might know about the Pauli exclusion principle in quantum mechanics. He once said of a misguided physics paper, "It is not even wrong." To a colleague whose paper he had reviewed, he said, "I do not mind if you think slowly, but I do object when you publish more quickly than you think." So Pauli being a bit, After he heard a confused, incoherent seminar, he would say, "What you said was so confusing that one cannot tell whether it was nonsense or not." When fellow physicists complained that Pauli was too critical, he would reply, "Some people have very sensitive corns, and the only way to live with them is to step on these corns until they are used to it." His impression of the unified field theory was reflected by his famous comment that what God has torn asunder, let no man put together. Ironically, later Pauli would also catch the bug and propose his own version of the unified field theory. So this is basically saying the unified field theory might be something that only God knows about. This is where, a lot of people who are cosmologists often, those are the famous scientists who end up debating some religious leader, for example, because this is where the universe, cosmology, beginning of the universe, this unification, the Big Bang, all these things is sort of getting really close to, well, should we even know these things? Because maybe God started the universe and we shouldn't know these things and stuff like that. Like, for example, the first 10 to the minus 43 seconds of this universe is the Planck era, where we don't know a lot about that era, and some people might be like, okay, it's okay that we don't know because maybe that is the wish of God. But at the same time, we would like to learn what we can and treat physics the way physics is treated, scientifically, and try to discover things and try to learn things. But of course, there could be things that we cannot know because it's too far back in time or too far away, and light cannot travel faster and things like that. So we understand that there are limitations of physical nature where we cannot sometimes know something. But at the same time, if somebody's trying to do a theory of everything, I don't know if it's enough to really say that, oh, maybe God doesn't want you to know that. I mean, that might have to be a slightly different kind of discussion, okay? So Pauli's view would have been endorsed by many of his fellow physicists who grew increasingly preoccupied with the quantum theory. So the other thing, of course, that was going on at that time was huge strides were being made in quantum mechanics. And even though a very bizarre world that was physics of the small, of course, it was successful nonetheless, because it went on to give us new discoveries, a better understanding of the atom, which of course, fundamental unit of matter. I mean, turns out that there are even more fundamental units, like there's a nucleus, there's things inside the nucleus, protons, neutrons. I mean, those even apparently break down into further fundamental units called quarks. But basically what I mean to say is quantum mechanics was making a lot of progress in the 20th century around this same time in parallel. And of course, because of its success, went on to give us particle physics as well. If quantum mechanics was unsuccessful, then we would not have this whole big field now of particle physics. And so what happened was, this general theory of relativity, the gravitation business, the classical physics, this whole dimension stuff, the geometry way of explaining unification, this was there, but people were getting more and more taken up with quantum mechanics, and later on, honestly, with whatever they needed to for the world wars. Remember, because, for example, that there was the race for the atomic bomb for the Second World War, and a lot of people honestly got caught up with all that. Okay, so anyway, because also, because the whole thing with radiation, Marie Curie, all that, everything kind of snowballed and took place in the 20th century. So that there's many different avenues for successful physicists to go into. They didn't have to get caught up with a geometry problem if they thought, oh my God, this is kind of going nowhere, Like, for example, what happens even now, like even now, there's fewer people probably working on string theory than there are on particle physics or experimental, measuring gravitational waves, for example, or even probably working on trying to understand dark energy, dark matter with experiments, right? So there's more people in these other fields because they maybe have more hope that those fields will progress, whereas this geometry issue, even though it's it's well motivated, the theory of everything has this big motivation, but people were getting caught up in other things. Okay, so anyways, the quantum theory stands as one of the most successful physical theories of all time. It has had unparalleled success explaining the mysterious world of the atom, and by doing so has unleashed the power of lasers, modern electronics, computers, and nanotechnology. Excuse me. Ironically, however, the quantum theory is based on a foundation of sand. By the way, this book is written by Michio Kaku. I'm filling in with my own comments and thoughts, but the book that we're reading from is called Einstein's Cosmos by Michio Kaku, who is of course a string theorist. So just keep in mind about these biases as well, okay? Let's see. So let's see. In the atomic world, electrons seemingly appear in two places at the same time, jump between orbits without warning, and disappear into the ghostly world between existence and non-existence. So he's talking about the uncertainty principle and all that stuff, probabilistic nature of quantum mechanics. Because I don't know if you were here. We've had this kind of discussion quite a number of times on these lives where people that are, the classical physicists, the string theorists, the general relativity, the geometry people, all these people don't really like the probabilistic nature of quantum mechanics and the uncertainty principle and all those bizarre things about quantum mechanics, even though, that is the physics of the very small, and maybe I think you do need those types of treatments there, but they just don't like it, okay? So they're saying there's definitely motivation to try to understand it from a different perspective. So, as Einstein remarked as early as 1912, the more success the quantum theory has, the sillier it looks. Some of the bizarre features of the quantum world were made apparent in 1924 when Einstein received a curious letter from an obscure Indian physicist, Shyotendranath Bose. This guy, Bose, is who bosons are named after. Boson is a type of particle, remember? The photon is one of the bosons. Whose papers on statistical physics were so strange that they were flatly rejected for publication. Bose was proposing an extension of Einstein's earlier work on statistical mechanics, searching for a fully quantum mechanical treatment of a gas, treating the atoms as quantum objects. So Bose-Einstein, or there's statistics. By the way, there are in thermal physics, if you take thermal physics, you will come across this topic of basically having a statistical analysis or statistical mechanics of things that you can just kind of treat them as one thing almost when they are all in sort of this same state, which is what is going on with this bosons at this time. Okay, so just as Einstein had extended Planck's work to a theory of light, Bose was hinting that one could extend Einstein's work into a fully quantum theory of atoms in a gas. Einstein, a master of the subject, found that though Bose had made a number of mistakes, making assumptions that could not be justified, his final answer appeared to be correct. Einstein was not only intrigued by the paper, he translated it into German and submitted it for publication. He then extended Bose's work and wrote a paper of his own, applying the result to extremely cold matter that hovers just above the temperature of absolute zero. So this is a very, very important topic that we're speaking of right now in thermal physics, and you can look this up. It's Bose-Einstein's statistics. We also have this type of thing with the other types of particles for fermions as well. Thank you, Tasty. Thank you, Ben. Thank you, ex-Christian. Yes, I did. My background is in particle astrophysics. Yes. Somebody asked. Ex-Christian Sophia is asking, "Are you an astrophysicist?" Yes. Frodo is saying you actually teleport something and you're not going to wonder if you're in a dream. Okay. Hi, Robnoxious. Okay. I'm gonna look at your comments in one more second. Okay, so let's just finish up this sentence, or this part. So Bose and Einstein, absolute zero would be absolute 0 degrees in the Kelvin scale, okay? So Bose and Einstein found a curious fact about the quantum world. All atoms are indistinguishable. That is, you cannot put a label on each atom, as Boltzmann and Maxwell had thought. While rocks and trees and other ordinary matter can be labeled and given names, in the quantum world, all atoms of hydrogen are identical. In any experiment, there are no green or blue or yellow hydrogen atoms. Einstein then found that if a collection of atoms were supercooled to near absolute zero, so you've really cooled these atoms, where all atomic movement almost ceases, all the atoms would fall down to the lowest energy state, creating a single superatom. So this is what I meant about that state thing, the thermal physics. So as you can imagine with intuition, like states of things, right? Like, for example, water has a state, ice, it can be a gas, it can be liquid, right? So this state stuff is important. Now imagine you've supercooled atoms to a very low temperature, just above 0 kelvins. The state that they all get into is their lowest excitable state or lowest energy state. And in that state, they're actually acting like one giant, one atom, if you will, a superatom. They're all indistinguishable. And you can basically write down equations for them by doing the statistics of these atoms and their properties in a way as if they're, first of all the same, and second of all, they've all become this super atom that's just kind of in that state together, okay? So these atoms would condense into the same quantum state. So that's the other thing. As we know, there are quantum properties and things like that, which one might be wondering about. But for these atoms, they will all be in the same quantum state, behaving essentially like a single gigantic atom. So we don't have to think about, oh, out of these atoms are some in a different quantum state than others. Well, because of the energy that they're all in, because they have been super cooled and they've all kind of fallen to their ground state or their lowest energy state, they will actually all have the same quantum state as well. And you can drastically simplify the way you write down the mechanics for these atoms at this point now, okay? By simply understanding that. And because, you know, people are interested in figuring out the mechanics and the how to write down the behaviors and change of position or change of something with time of these things, of pretty much anything in the physical world. And so for these atoms, we would want to know. And there's a lot of atoms. So if they're all different, then that would have been vastly more complicated to write anything down for. But if they're all actually the same, and now they're all actually behaving like one, then you can imagine how that kind of makes it possible to write down your equations. So there's this, you'll come across Bose-Einstein statistics, fermion statistics. You'll understand those types of, you'll come across those types of things in those classes sometimes. And essentially that's what this is, okay? So you can kind of start to have simplifications in your statistics and understanding because of that. So, however, so anyway, these atoms would condense into the same quantum state, behaving essentially like a single gigantic atom, which also means that you only need to write down equations for that single gigantic atom and you've understood the whole system. So he was proposing an entirely new state of matter, never seen before on Earth. However, before the atoms could tumble down to the lowest energy state, the temperatures would have to be fantastically small, much too small to be experimentally observed, about 1/1,000,000th of a degree above absolute zero. At these extremely low temperatures, the atoms vibrate in lockstep, and subtle quantum effects only seen at the level of individual atoms now become distributed throughout the entire condensate. So this would be the Bose-Einstein condensate. So what's so nice is that these, when you do achieve this Bose-Einstein condensate state, which is only possible if you go to the very extremely low temperature, the nice thing is that there are certain subtle quantum effects which would be seen at individual atoms, but now you can see it for this entire thing distributed throughout the thing. So, like the spectators at a football game who form human waves that sweep across the stands as they stand up and down in unison, the atoms in a Bose-Einstein condensate act as if everything is vibrating in unison. But Einstein despaired of ever observing this Bose-Einstein condensation in his lifetime, since the technology of the 1920s did not permit experiments near absolute zero. Those temperatures were unattainable at that time. In fact, Einstein was so ahead of his time that it would be about 70 years before that prediction could be tested. So they worked on the Bose-Einstein condensation equations and what this whole situation would be. And isn't that interesting that Einstein worked actually quite a bit on quantum mechanics, given how much he critiqued quantum mechanics and wanted a whole new theory of everything, which would subsume quantum mechanics. But actually, he contributed significantly to quantum mechanics. This is one example. And of course, photoelectric effect is what's considered the old quantum mechanics, where we apply the quantum nature of light. So that's what I find funny as well sometimes, that Einstein actually has a number of contributions that are outside of relativity and outside of the classical physics stuff that he's known for, such as these examples, okay? In addition to Bose-Einstein condensation, Einstein was interested in whether his principle of duality could be applied to matter as well as light. In his 1909 lecture, Einstein had showed that there was a dual nature to light, that it can simultaneously have both particle and wave-like properties. Although it was a heretical idea, it was supported fully by experimental results inspired by the duality program initiated by Einstein, a young graduate student, Prince Louis de Broglie. So this is spelled as Broglie, Broglie, but really it's Louis de Broglie. They then speculated in 1923 that even matter itself can have both particle and wave-like properties. So by the way, Louis de Broglie wrote the matter-wave equations that we learn in quantum mechanics. Now, those were taken and further work was done on them, and that's another whole thing. But yeah, this is the de Broglie name is important in terms of whether matter can be written as waves. Okay, this was a bold, revolutionary concept since it was a deep-seated prejudice that matter consisted of particles. Let's see. Stimulated by Einstein's work on duality, de Broglie could explain away some of the mysteries of the atom by introducing the concept that matter had wave-like properties. So Einstein liked the audacity. So all of these people, by the way, they all got Nobel Prizes. We will get into the stuff that Dirac did with the de Broglie equations probably next time. But basically they took, Dirac actually took the matter wave equations and turned them relativistic to get his version of the equations. So relativistic equations of particles gives you the next stage. But the fact that matter may have a duality as well, where matter can be both particle and wave-like, this concept came from Louis de Broglie. Okay. So anyway, de Broglie eventually got the Nobel Prize for that idea. And then we actually launch into a bunch of quantum mechanics. So I'm thinking the next portion is actually great. I want to go over it in more detail, in more time, probably next time. So next we're actually going to talk about Schrödinger, Dirac, Heisenberg. These are all guys, of course, that contributed a lot to quantum mechanics. So I want to take my time when I tell you about that. So basically we're seeing that there was special theory of relativity, general theory of relativity, big motivation to get a theory of everything, which would unify gravitation and electromagnetism in those days, because they didn't have all the rest of the fundamental forces that came later. And also because of bizarreness of quantum mechanics, certain things that people didn't like, probabilistic nature of quantum mechanics, uncertainty principle of quantum mechanics, they didn't like it. So they wanted a theory of everything, or a overarching unified field theory to be able to explain everything. But along with that, we also see certain people getting distracted because they go towards more and more of the quantum mechanics efforts, and also the wars happened, and some people had to help out with that, or they were made to help out with that. Then comes this whole side project of the Bose-Einstein condensate, which was actually a really big deal as well, because it goes on to give us statistical physics or thermal physics, and like the entire field of thermodynamics was changed forever with that. And then we come to basically, just like Einstein gave light, that there's a wave and a particle nature of light. Somebody, de Broglie here, suggested the same thing for matter, and writing down equations now for matter in that way. Actually, Schrödinger will be the one that writes down the wave equation for matter. and then Dirac will turn them into relativistic equations, and then someone else, was it Heisenberg? I think Heisenberg will turn it into probability, or no, sorry, Max Born. Max Born will turn them into the fact that actually the wave equation is the probability of finding the electron, not the true position of the electron, because you can't know the true position of the electron, things like that. And then of course Heisenberg will do some things and Niels Bohr will do some things. So pretty much there's going to be a number of people we mention next from that same century. So it's going to turn into this discussion of the 20th century, which is a very rich period of time where, of course, along with relativity and all of these things, we also got great progress in quantum mechanics. So I don't want to rush through that. We will pick that up tomorrow. But I also think that it's funny how intertwined certain things can be, even though these people were sort of not happy with how things were turning out and how quantum mechanics was different and new and weird. But also a lot of those same people actually contributed to quantum mechanics. So yeah, the drama unfolds, and the drama can be also a little bit unpredictable, as in it might be different from what you might think as far as those days, okay? So we will do that next. We will talk about de Broglie, Schrödinger, Dirac, Max Born, Heisenberg, and Niels Bohr next time, who are all people who made progress and gave us quantum mechanics the way we know it in the 20th century, okay? So we will talk about that. There's actually a really good story of the debate between Einstein and Niels Bohr as well, I believe, in this same chapter. So we will cover that. And I will further talk about this tug of war between quantum mechanics and classical physics in that century. But as you know, of course, quantum mechanics kind of wins in that sense that it continued to be successful and it gave us particle physics and it continues to be a thing. But it's always entertaining to go back and look at the progress of both, okay? And also for the people who like string theory and quantum gravity and all that. So there's really those aspects, right? We can think of, basically in this channel, we talk a bunch about these things. Cosmology, we've covered dark energy, dark matter, how those are, of course, unsolved mysteries, currently topics of research. We've talked about astrophysics. We talk about astrophysics and astronomy a lot as well. You know, all kinds of things, stars, supernovae, galaxies. But basically, the recurring topics that come back up a lot is the one that we're talking about right now, this motivation for a theory of everything, relativity, quantum mechanics, and how this leads to string theory and sort of the basis of string theory, as well as what are the limitations and some more details about superstring theory, okay? So for the people who like that, I have a number of episodes on superstring theory. For the people who like astronomy, astrophysics, I have many episodes on that. And this topic, we have also actually covered all of it in the past, but we're kind of going over it again because it's interesting. Thank you everybody so much for joining. I will look at your messages and then go to bed, okay? Thank you everybody. I've been a bit under the weather, so my lives have been a little, you know, here and there, but I hope to come back in full force starting tomorrow. So I hope that I see many of you joining again live. Please do like, share, and subscribe. If you subscribe, then I hope to see you again in future lives, and you can contribute to those lives, and we can have a lively discussion during those lives. And I generally interact with the chat a lot more. especially when I start the lives at a, more regular time. So if you subscribe, that's great, because then I keep seeing you in the lives, and we can continue this topic. Okay. Thank you, Rapinter. Rest more. Bye. Get better soon. Thank you. Thank you, everybody, so much. Thank you for the likes and the shares and the subscribes. Really appreciate it. Would like the early like today. Would like the early live today. Yes. Thank you so much, everybody, for liking and subscribing. Really appreciate you. And yes, I need to start the live a lot earlier. Yes, for sure. I almost did not go live tonight, but then I was like, I just want to do at least a little live. Shalom. Good night, good morning, good afternoon. Salam. Namaskar, everybody. Namaste. Thank you, BMCK. Thank you, Milu. Hope you feel better. Thank you so much. Thank you, thank you. Hi, Jerry. Hi, Mike. Hi, Flying Huckleberry. Thank you, Milo. Hi, Raphael. Hi. Hello, Raphael, my friend. How are you? Hello to Switzerland. There's so much we don't know. Yes. Mass Mayhem, how are you? Hi, Adeline. Much prosperity and abundance. Thank you, young Nabila. How are you? Hi, Samuel. Samuel is saying to talk about telepathy. You prefer trains. Hi, Joey. Intelligence is attractive. Okay. Why don't you talk about telepathy and the sixth sense? Telepathy and the sixth sense. Okay. Many of these people that we mentioned are German, yes. Yes, indeed. Isn't that crazy? That some of these people who were all sort of, it seemed like almost like working together, but they were all split up during the World War. Many of them were split up. Of course, yeah. Lots of things happening in Germany. Of course, good physics happening in Germany as well at that time. His favorite smart person on YouTube. Thank you, BMCK. Thank you so much. Really appreciate you. Hi, Neil. Hi, Yep Yep. I feel like I haven't seen you in a while. Hi, Godzilla. I'm glad you learned so much. That's great. Thank you. But Oppenheimer. Oh my gosh. We will we will definitely talk about Oppenheimer as well. I should make a note. You have really big eyes. Hello, AA, DA. Do I have big eyes? I feel like they look kind of small right now, actually. Position momentum. Yes. Oppenheimer. So, you know what is a shame? I haven't seen the movie yet on Oppenheimer, but we will definitely talk about Oppenheimer. Heisenberg. You will definitely see how there is a chapter on the Second World War here, and we we hear about these same guys in that one too, which is very strange. So much really happened in the 20th century, you know. Makes you wonder sometimes, what are we doing now? But I know we're doing a lot now as well. We're doing, you know, we're measurements and experiments and precision. Astronomy is sort of where we are at this time. So, and of course, like the laser stuff and like really like the Bose-Einstein condensate and those things that we just talked about. Those are incredibly important in today's technology. I hope you know, like, you know, all this stuff about lasers and whatnot would never be, you know, it would not never be possible without all that work that these people did. So I'm not much into lasers, but um, there's a lot going on in those worlds as well. The atomic, molecular, and optical physics world, thermal physics, or what do you call, condensed matter physics, those like material science type of things, really, really, really care a lot about this, you know, the Bose-Einstein condensate, and these type of statistical physics that we can get into, because I'm glad I came across your channel. It's extremely refreshing. Thank you. Hello, friend zone millionaire. Subscribed. I have to get back to the stock market. Keep on, my brilliant young friend. The stock market is not open yet, is it? At least in the US. Based on research, the experiment involving 37. Hi, Joe Jones. Okay, so top fans right now are number 1, Ben Abraham. Thank you, Ben. Number 2 was Dilshod. Hi, Dilshod. Number 3 is Christ. Jesus Christ himself is here. Number 4 is Milo Torres. Number 5 is Mr. Apple. Number 6 is Friend Zone Millionaire. Number 7 is Raphael. Number 8 is Robnoxious. Number 9 is Mass Mayhem. Number 10 is Junaid. Thank you guys all so very much for joining. And thank you, J-Dub. Became a member. Thank you so much. That's a great way to support me. It's a monthly membership, which is very cheap at this time. So there is that. Talking about this stuff got me kicked off of LinkedIn. A year later, Elon Musk was talking about AI server farms in space. Hi, Friendzone Millionaire. I see your comment. Hi, Robnoxious. I see a lot of my old friends here as well as some new ones. Thank you, everybody. Welcome to the channel. Yeah, we have also talked about Neil deGrasse's books recently. And then people mentioned Bill Nye. Love all the comments, guys. Appreciate it. Okay, so we will keep on keeping on tomorrow. Let's see. If you see our other videos, please do give it a like, show some love, appreciate it. We will come back with a live tomorrow night, starting it earlier. And if you see our shorts, clips, videos, anything else, pre-recorded videos with the live chat, please show it some love, appreciate you. It requires great knowledge to understand. Okay. This topic that we're covering right now is probably my favorite topic. I want to cover it with more energy and expression tomorrow. See you next time, Ben. Hi, Delilah. Start young and invest in Roth index funds. Okay, very nice. Hello, Don Ricky. Hello, Retta. Hello, Blue Sentinel. I like the financial advice as well in the comment section. If it's AI, I like it. Okay. Can you say hi, Delilah? I'm OTP with my friend, and she asked if you can say it. Hello, Def Not K and Delilah. Food stamps. Why do you look like you're gonna talk about American politics? I almost never talk about politics. But thank you for being here. Hello, John. Hello, Q. Salimic Q. Hi, Giovanni. How are you? Hello, Baba. Thank you, young Nabila. John Ramsey. There's Baji. Do you like statistics and data science? I do, yeah. Not more than physics, but yeah. Statistics and data science. Statistics and data science are a part of physics research. So especially if the goal is, some discovery in physics, then I would really like statistics and data science. As a job, working at a company, I've done those things as well. And those are fine too. I mean, good. I like technical work, so it's nice to work on something like that. But at the same time, if it depends on your motivation as well. Like, I don't want to do a bunch of data science without a really good motivation. So as much as I like the technical work, it's also nice when the motivation is something really inspiring. You know what I mean? And so yeah, yes, the short answer is yes, I do like statistics and data science. I have to. It's part of life. So 20,000 people are, oh gosh. Thank you, Milo. You're very beautiful with impeccable, intelligent manners. Thank you. That's nice. Hi, Nico. My major used to be physics, physics, and physics. Well, I majored in other things too, but that's the major I actually finished. All my degrees are in physics. I majored in some other subjects as well, but the finished degrees are in physics. Oh, really? I didn't know about that. I did not know that about trolls. 80% of most trolls are 12, 13, and 14-year-olds. Aw, little babies. Hello, Abbas. Oh, do you do data science for fun? Thank you, guys. Appreciate all of you. Wait. Thank you, Sean. How many articles in journals? I'm trying to think if there is a consolidated list of my papers handy right now. Well, you know what? Let's see. Let me just share. Maybe ResearchGate or something might have it. I'm not entirely. Oh God. The website is making me verify myself. 20 people. Oh man, this is somebody else. Let's see. Going skydiving tomorrow. Gotta sleep. Love your streams. Thank you. Please be safe skydiving. Triple major in computer engineering, business management, and aviation. Oh, I love it. Do you fly planes for fun? I need a pilot. Okay, so thank you, Valley Legend. Best. A pilot. I was asking someone that just mentioned their aviation things about if they're a pilot. So let's see. Couldn't answer my question. Jarrell, what's your question? Oh, sorry, I didn't see it. I see it now. I have a question. 50 subs and I'm trying to go live, but it's telling me to create more shorts and gain 50 subs. Did you do your identification verification, by the way? I know that I think for going live, I had to do that step. I did go to Cal Poly. I visited Cal Poly for a collaboration meeting. Hi, Suji. Suji, the kitty cat, is on top of my kitchen cabinets. Thank you so much. Oh, no worries. Half the time I can't see the comments and you know, they pass too quickly, and I definitely cannot tell if someone is black, white, or orange, you know. But I'm glad you said something, so I got to your question. Was wondering for my daughter. So Cal Poly, right, in San Luis Obispo, right? Cal Poly. So I do believe it's a great school. I know a professor. She might have now gone to a different school, but she used to teach at Cal Poly. I mean, she's one of the best I know from particle astrophysics, and she, I believe, now teaches. She is a professor somewhere else now. Dr. Steph Whistle, if you look her up. And she used to teach at Cal Poly, and she hosted a collaboration meeting when I was a grad student, and we all went there, and it was a lot of fun, and we did wine tasting and kayaking in the Pacific Ocean, which kind of scared me, actually. And we had a lot of fun, so it's a good school. So yeah, for the going live, I think I would keep posting shorts. I think they really want that from small channels. Lately, my shorts have been getting very low views all of a sudden. I don't know what that is about, but that can happen sometimes. YouTube just has bugs, or it's just pushing different things and it doesn't want to push certain other things, you know. So I mean, there's been a lot of ups and downs with things, and it's never quite obvious what's going on. But yeah, one thing I can think of is I think you need the ID verify. Like, they need your actual ID and want to make sure who you are and stuff if you want to go live. Other than that, I think I probably already had quite a few subscribers when I was trying to go live. When I was trying to go live, I remember I just had to do the ID verification. Pretty much that was it for the question about the lives. Grady is here. Hello, Grady. Hello, Triana More Land. Hello, Alfie. So, okay. So hopefully couldn't answer. You made the right choices in life. Someday you'll be appreciated by all the universities. Thank you, Northern Versus. Appreciate you. Thank you, Valley Legends. Hello, Saddam. Okay, so everybody, and what was your question? The person, she needs to start her graduate classes. I think Cal Poly is for undergrad only, right? I could be wrong, just double check, but I think Cal Poly might be for undergrad. So there is that. Okay, so please come back tomorrow to tomorrow's live, and we will pick it up from there, okay? And if there were questions that I missed tonight, please bring them again tomorrow night and just uh, tell me or the mods and just poke the chat so that I can definitely see your question and get it addressed. Okay. Thank you so much, everybody. Really appreciate you. Thank you so much, and good night, and see you soon. Mwah, mwah, mwah. Thank you. Love you. Please do like, share, subscribe. And also, if you see my shorts, clips, videos, other things, other posts, videos, whatnots, please do engage with them, interact with them, because I don't know why my shorts are quite low views right now. It's fine, and whatnot. Lovely to see you all.